All right. So welcome back, everybody. We just had a wonderful time here at JPL doing Strange New Planets and exploring some, until today, undiscovered solar system bodies and coming up with some plans for how we could find out more about them. So we are readying to shift over from JPL to the University of Arizona to the OSIRIS-REx offices. And I wanted to introduce myself to, I know I can see Ross there is getting everything all set up. See you. That's it.
I'm assuming you can hear me over there, right, Whitney?
So I'm going to just say this. I'm assuming that everybody at all sites is hearing this. So I'll just say we're going to be turning it over to the University of Arizona. My name's Whitney Cobb, and I just wanted to introduce myself to the presenters at OSIRIS-REx because I am sort of an informal moderator. I'll mostly be listening and learning just like everybody else, but I just wanted you to know who I was in case a question came up. And I'm going to pass it on to Anna or to Ross, who can introduce our speakers.
You have a light on the panel.
Can you hear me?
We're going to do that as well.
Can they hear me?
Yes.
Testing? Oh, wait, no, we're playing music here. Testing microphones over here at the University of Arizona.
Can you hear us? At least not there anymore.
Have them flashing.
If you hear us, please clap. It was a great round of applause to welcome us. Thank you very much. I'm Anna Spitz. I'm the EPO lead, Education Public Outreach lead for OSIRIS-REx. Ross is the EPO coordinator and the guru on our technology. And we're very happy today to have this wonderful panel. They're representatives of our OSIRIS-REx camera suite, which is one of the instruments on OSIRIS-REx. And they're going to give us an overview of OSIRIS-REx, a quick overview of the mission, and then talk about what each one of them does on the mission, and then how they work together on the mission. That's really the crux of how our scientists and engineers work together to make this mission go. And we have Bashar, Rizk, Ellyne, Kinney, Spano, and Kat Merrill, Merrill. And they all represent different elements, but they all know a lot about it. So I'll turn it over to them. Thank you.
Good morning, everybody. I am Kat Merrill. Next slide, please. So we are part of the OCANS team, and we are on the OSIRIS-REx mission. The OSIRIS-REx is our sample return mission from asteroid 1999, RQ-36. We're launching in 2016, and we do rendezvous with the asteroid a few years later and then return back. We return back some regolith to the Utah test site. Next slide. So 1999 RQ-36 is one of the most hazardous asteroids in the cosmos to us. It also is a carbonaceous asteroid, and it is very interesting for multiple reasons. It was selected a few years ago as being an asteroid that was interesting enough to go and sample, and so that's our targeted asteroid. This is the spacecraft. You can see for scale's sake, we have Ross standing next to our TAG-SAM arm. This is the arm that when we don't hover, we actually go down to the asteroid and we touch and go. And this is our touch and go sample head that Ross is standing next to. We touch the asteroid for a very short period of time, exert some gas, and we basically vacuum up some regolith, and then we store that. In order to do that, next slide, we have to do several different functions. First, we have to get to the asteroid, so we have to find it and find our way there. We have to map it. Then, and at that point, during the mapping process, where my colleagues are especially useful, they're on the science team, and so they get to do a lot of the selection of the sample site. then that sample actually has to be returned, and then we curate it and learn from the sample itself. So my name is Kat Merrill. I come to University of Arizona from Raytheon originally. My master's is in optical sciences, and prior to starting this job, I never considered myself an engineer, but my role on the team is to be the lead systems engineer for the OCAMS instrument. It's the mission critical instrument, one of two on the spacecraft. As the lead systems engineer, my job is to make sure that we have requirements so that we know what we have to do. And then I also have to be in charge of making sure we know that we can do all those things, so the verification of those requirements.
And I guess it's my turn. I'm going to introduce myself. I'm Bashar Rizk. I'm the OCAMS deputy instrument scientist, and I'm also on the systems team with Kat. And basically my job is very similar to Kat's. We're trying to translate the scientific goals of the mission into requirements, and the requirements into a design, and make sure the design fulfills the goals. So we try to complete that loop, and Ellyne's going to talk more about that in a bit. Ellyne?
Sure. My name is Ellyne Kinney Spano. I'm the image processing scientist on the team. Because I'm working with the images so much, I work very closely with Kat and Bashar on how the camera works and operates. And I just have a little graphic here that gives you an idea of what we do to get those images. It's not like a point-and-shoot camera that you might use for yourself. The cameras that are used in space are pretty highly specialized, and they're also in a very harsh environment. They're subject to radiation, to extreme temperatures, to vacuum. And so up in the upper left, I have a raw image that has quite a bit of noise in it. We need to take that noise out. We get a corrected image. We actually don't get color images, we get black and white images. And so in order to acquire color, we take images with different colored filters in front. And so I have a graphic here of the color bands. The colors in these pictures are actually quite exaggerated, but to give you an idea, we have one that's taken with a red filter, a green filter, and a blue filter, and they're combined to make a color image. And then we take all of these smaller images and we make a big, huge image mosaic in order to get a high resolution, full coverage image of the entire, this is just one side of the asteroid here. And then from that image, we're going to go ahead and we're working with the U.S. Geological Service to actually turn these images into maps so we can figure out where we're going on the asteroid. And so the various scientists that work with us on this mission are going to get together, pore over these maps. There's going to be some process to decide exactly where we're going to go to take the sample from.
Sounds useful. So this is a presentation or a picture of the three cameras that we're building on the OCAMS team. I like to think of them as three sibs. The oldest is the map cam, which is in the middle. It's designed to map the asteroid and has a medium-sized field of view that's useful for that purpose. It also can function as a backup in case the polycam, which is the telescope that you see behind me, fails to function. The polycam, well, if I point it, will they see it at the other side? Okay.
No.
I'll just gesture a lot, and hopefully you'll. I could do the interpretive dance. The polycam, which is the telescope and the largest of our three cameras, is designed to view the asteroid from long range, and it's also designed to view it from a couple hundred meters away, which is the size of basically 2 football fields, and examine whether we have pebbles small enough to be ingested by a TAGSAM head on the surface of the asteroid. The last camera, which is the smallest of the three cameras, but also has the widest field of view, is the SAMCAM, and it comes into operation when we will actually take the sample, when we actually perform the touch-and-go maneuver, and it documents the maneuver, and then when we pull away with hopefully our sample, it'll observe the TAGSAM head and see the evidence that we've acquired the sample, and also make sure that none of the pieces that we've acquired of the asteroid are so big that they'll prevent us from putting the sample back into the canister for the trip home.
So, sure. We just wanted to describe a little bit about how engineering and science work together to make this happen. And back several years ago, things worked a little differently. Projects were a little smaller, and what often would happen is a scientist would go into a lab have a few people that worked with him, and they would just go, or her, and go ahead and just build the instrument start to finish and use it. And as projects got more ambitious and bigger, this started to not work really well. Projects started to go really over cost and over schedule tremendously. And so we had kind of an awkward adolescence phase where the engineer said, hey, we can help you with this. We know how to build things. And so the scientists would give requirements to the engineering team. And then the engineering team would go off and take those requirements and build something and give it back to the scientists. And the scientists would be like, okay, that's what we asked for.
That's not what we wanted.
It's not what we need. So then what we've grown into is this modern design process where the scientific goals are laid out and identified in the beginning. We then analyze those and come up with actual specific requirements that the engineers can then go and start making some prototype designs on. Come back and say, well, we kind of could get this to work, but this didn't quite work the way we thought, and is this really what you want? And the scientists can look at it and say, okay, we can sacrifice on this one, but this is really important. We have to figure out how to make it work. And we know we told you this, but we really meant that. And we kind of closed the loop now. And so there's this process, this iterative process. And as we get closer to actually building this, we should all converge on the same page and make something that's going to really work on time, in schedule, and do what it needs to do.
And you can think of that circle, if I may make a comment,
yeah.
You can think of that circle as being operated every day, all the time, 24 hours, to constantly analyze whether the requirements fulfill the design, whether they don't blow out of the cost box or the schedule box. So all three of us, and in fact, all of the engineers, I would say, on the project, have it embedded in them that we can't blow cost, we can't blow schedule, but we have to fulfill the requirements and come up with a reasonable design. So I think that process has probably come to a...
And not only the engineers, but the science team also realizes that we have to think about what we really want. And if it's going to be this expensive, you have to look at it and say, well, how much value does it bring to the mission? You can't just say, well, I want it. You have to actually say, we need it because of this, or, oh, gee, this would be nice to have, but I didn't realize it was going to cost that much. And Kat's really good at making it clear to us what it's going to cost.
So one of the challenges that we had is when you first propose a mission, you think you know what's going to happen and how you're going to work the mission. And then you start defining requirements based on how at the time, your best knowledge of what's going to happen and what you're going to need. But over time, you learn more things. The previous presentation, we saw that there were more images of the moon now where we can say, hey, we wouldn't actually want to land there. Well, if you didn't know that when you wrote your proposal, you wouldn't know that in your early requirements, and you wouldn't necessarily use that in your early designs. But later on, you might have to say, well, can the design meet this new scientific goal or scientific requirement? And so we work with that every day. And then you also we're at this point in the program where we're starting to build the prototype hardware. And so it's really where the rubber meets the road of, this is really what this thing can do. And so at first, it was the science team saying, this is what we need. And then we said, well, this is what we can give you, really. We wanted the design to do all this stuff, but this is really what we can do, given all the constraints that we have. Can you make this work? And so this is where the three of us are working a lot together to make sure that as the design matures and the science matures, that they're still going to overlap and be useful instruments. In some cases, it's changing the use of the instruments. At one point, the Polycam had very specific places where we were going to take pictures, and now there's a whole range of places that we're going to take pictures. And originally, some of the people thought that was a little risky, but now it's part of the mission.
Goals evolve.
And so as the goals evolve, the design evolves. And
thank you for not making the childlike gestures too childlike when you're describing the scientist. We appreciate it. We should take questions now, don't you think?
So we're really interested in people's questions about the design process and how groups of people with different backgrounds work together.
Yeah.
So we just did an experiment where we're looking at the different planets and choosing a landing site based on that. And you mentioned that one of the things you're looking for in your site is pebble size so that you can actually collect the sample and go off with it. But what other things are you guys looking for?
So we're looking for several things. The first one is the safety of the spacecraft. We need to make sure that it can actually sample there safely, so we don't want it to be next to a crater.
Or a boulder.
Or a boulder. We're looking for something of scientific interest, and this is where the color maps that Ellyne showed us are useful, because we can see different elements and find out, because if you can find something that's, sort of one type of material, it might not be as interesting as finding ones with multiple types of materials.
This mission is all about the materials that made up life. We're going to a carbonaceous asteroid. We're all made of carbon. So if we can identify a region on the asteroid that is potentially carbonaceous or potentially contains volatiles, that will be our preference for where we go. So that's kind of what's informing the color measurements we're making. You want to add anything?
No, that sounds great.
Yeah.
Two questions. One has to do with the autonomy of the spacecraft, or what kind of time lag exists between commands from the ground. Is it operating autonomously? The second one has to do with the quarantine of organic material once it comes back to Earth.
So I'll start the first one, then we hand it over to Ellyne, because she knows more about that than I do. But so when we plan the mission and when we plan our design, we plan to run on a series of sequences that are uploaded. So they're tested on the ground before they ever get to us. And then, so our cameras don't operate autonomously, they're operated from ground sequences. But I'm going to hand it over to you guys.
So I think Keiko is going to talk more about the curation, and she's expert on this, but I'll give you a quick summary right now. Of course, if you bring something that potentially has carbon or the precursors of organic life, volatiles, in it, you want to make sure when you bring it back to Earth, it's really easy for all of the carbon and life and organic material here on Earth to contaminate that sample. And so we have this little sample return canister. On the picture of the cameras, it was sort of the dome-shaped thing that was in the background, and we place it in there, and we take pictures to make sure that it sealed it properly. And this actually was something that was used on the Stardust mission when we were returning a sample from a nearby comet. And basically, it gets the spacecraft comes back near Earth, and it basically shoots this canister back, and it has to be designed so that it won't break open on impact. And then there's
Mention the light travel time. 15 minutes.
Go ahead.
Well, I was just going to say, in answer to your question, it's a 15-minute light travel time when we get to the asteroid. So the possibility that we could have ground in the loop, which means we could get data back and then act on that data, is a real possibility. We considered it.
But it's basically autonomous.
It's basically not. I mean, it's open loop. There's a few autonomous features, but there's been a real tendency on this mission to get away from autonomy to the degree that we can, because it's very difficult to test.
If this spacecraft is coming down and you can't guide it with a joystick, obviously, that's
Right.
what I'm getting at.
So
What happens? Well,
we go through a series of maneuvers as we approach the asteroid. Once we get through the mapping function and we've identified our sample site, we go through a series of sorties to go down and test the sequence that would get us to the asteroid and back. We go down to 100 meters.
yeah.
And then we fly back out, then we go down to 30 meters, take images to make sure we're matching the velocity of the asteroid, and then come back out, and then we go all the way down and we do the tag.
And gravity takes us the rest of the way. So you just basically cut your engines and let it pull you.
But it's all sequence driven based off of knowledge that the science team will have, and they'll test the sequences here and then they load them up. But there are very few autonomous things that the spacecraft does. It does have some autonomy when it comes to the touch and go itself, because it has to know when it's touching the asteroid, because we do not contact it for a very long period of time.
We're going to need to touch base with some of our other sites right now for
Sure.
questions, I think, and then we can maybe come back here.
Yeah, so if you have other questions, feel free to write them down and then we'll come back. You want to turn it to Whitney? Is she gonna?
Whitney, I believe since you're our moderator, you're going to go around and check the other sites for questions there might be, because I know we have plenty more here at the U of A, but we don't want to monopolize all the time there.
Your generosity. So we are going counterclockwise, so that would make it Johnson Space Center. Does Johnson have any questions? And you know what? It would be wonderful if we did the split screen so we could see the other sites now. Ah, perfect. So,
Okay, I have a question. How deep do you expect the sample to penetrate? I mean, is it a matter of centimeters as you pull the sample out?
Just a few inches.
Yeah, we're dealing with regolith, which is, loosely held together rock. So we don't believe we're going to push very, very deep, but it is, one of the unknowns that we have to deal with, and it's a challenge that we have to face and design the spacecraft to handle. But we're only expecting to touch and go on the surface.
all righty. So, APL, do you have a question?
Yes, we do. You made mention that this was the most dangerous asteroid to Earth. How so?
The chances of this asteroid striking the Earth in the next 200 years are higher.
Microphone after the question's been asked.
Okay. The chances of this asteroid striking the Earth in the next 200 years are higher than that of any other asteroid.
But not until the late.
But yeah, there's. We could go into the detail of it, but yeah.
What's the percentage of that?
We have one more question. Can we ask it?
Go ahead.
You mentioned that in your design you chose to go by touch and go rather than landing on the surface. What was the criteria to decide on touch and go? And secondly, if the sample is lost, do you have the capability to go back and choose another sample to get with you?
So the criteria for touch and go rather than landing on the surface was because nobody could think of a scheme that would anchor us to the surface that was both cheap and not require a new development. Also, people were uncertain as to what the composition of the asteroid would be, whether we'd actually be able to sink something that would anchor us to the surface. And the answer to your second question is yes.
I think Ellen can go into more detail.
Okay, remind me again the second question.
In the second question, I mentioned that if the sample that is being pulled up initially slips and falls, then were you able to go back and possibly choose another sample to take with you?
Yes, we do. So there are multiple ways we could not get the sample, and one of them could be that the material, the site where we first choose may not have material small enough. We're going to do our best to get pictures that really give us confidence that that can happen. But if anything happens that, we don't quite capture the material, or there's some big rock that blocks our ability to close the sample head or put it in the canister, we have basically 3 chances to take a sample with this scheme. And the thing that is limiting that is we have the nitrogen gas that kind of gets released and kicks up the regolith so that it can be captured. And we have 3 of those bottles on board, and so we have 3 chances to make this mechanism work.
So, for example, as to how that led to a requirement for the camera systems is that if regolith comes up to the cameras, it could make the camera surface dirty, for lack of a better term. And so we actually had to design the SAM-CAM to have at least 3 filters that can be moved into place so that we can always get a pristine look at the asteroid surface so that Ellyne and Bashar can process the data.
Very cool. JPL, any question? Miko? Thank you.
Hello, can you hear me? What's the anticipated speed while you're passing by, and what will make you happy to find from there?
Should I get it?
Yeah, go ahead.
When we fly by the asteroid, we're moving very slowly. Remember, this is a very low gravity object, so it doesn't take much to stay in orbit around it. So I would say roughly 20 centimeters a second down to about 5 centimeters a second. So basically, let me think of something I can drop here, like that. If you hit the asteroid, it'll be moving at approximately the speed that my cup was moving when I dropped it. And what was the second question? Sorry.
What are you looking for? What do you want to find when you get to the site?
You want to take that one?
I think we're wide open on that. We would love to see carbon. We would love to see volatiles, and when we mean volatiles, we mean things like organic oxygen type material, water. I mean, I think we would be thrilled to find anything that we would recognize as something that would support life here support life. You know, the hope is that the theory is that these carbonaceous asteroids and the meteors associated with them are what seeded life here on Earth. And so anything that gives us evidence that theory is on the right track would be very exciting. On the other hand, if we find something totally unexpected, then we'll have to revise our theories, and that's even exciting too. So I think that there's a lot of value that can come out of this, no matter how it plays out.
All right, we have one more question here at JPL.
Okay, you said it's hazardous to the Earth because it's the one that has the greatest chance of, getting close enough to actually hit us in the next 200 years. If you had to quantify that, what would the odds of that actually happening be?
Right now, the published result says that that there is a chance of 1 in 1,800 that could happen. Go ahead.
In the late 21st century. Anna wants us to make sure we emphasize this isn't happening imminently.
Right. It's sorry. I don't want to scare anyone.
That's the late 22nd.
It's a 2180?
2180.
Yeah, 2180 encounter.
But one of the other goals of the mission is that, we do our best to know the orbits of these near-Earth asteroids as well as we can, and yet
that's a good point.
They're small bodies. This body is dark. It means it absorbs a lot of radiation from the sun, and actual, sun striking it and it radiating the heat away when it spins and turns away from the sun and is no longer getting heated is enough to perturb that orbit. And so one of the goals of the mission is to try and understand that process so that we can get even more accurate orbits, and that hopefully this will apply not just to this one asteroid, but to several of the other asteroids that are near
That's
Earth.
good.
To do that part of the mission, it's called the study of the Yarkovsky effect. We have other people who are giving instruments to the spacecraft, including our brethren over at ASU, and they're giving us O-tests, and that's one of their jobs on the mission.
O-test is a thermal spectrometer that's going to measure directly the radiation coming from the asteroid.
Excellent. Now, are there any more questions? We've actually got a whopping 2.5 minutes. Ooh. Now we have something.
on the screen. We have more questions at APL.
Here's my question. Hi, this is Anna. Here's my question. Once you have the sample and you've gone through it, what are the next steps for that sample? Would you use it potentially in other areas like agricultural based or scientifically based for finding cures or preventive measures for diseases? What are the next steps for that sample?
Actually, the preponderance of the sample that will be collected from this asteroid will be archived because we're pretty much guaranteed that the means we have of studying the sample right now are not the most sophisticated that mankind will ever, or womankind, will ever have available to them for the next 100, 200, even 1,000 years. And this experience was first realized with the Apollo moon samples, where we're still studying those rocks. It's been 50, 60 years now since we gathered them. In terms of the second part of your question, it's believed that this asteroid, which has been in orbit around the sun for hundreds of thousands, even millions of years, has been irradiated by galactic cosmic rays, solar protons, solar neutrons, and is therefore sterile. So there aren't believed to be any organisms that are alive on this asteroid that might perhaps be the source of a cure of the kind that you mentioned. Did I answer your question?
Thank you, but I'm thinking of more things we can get to after the whole show today. Thanks.
All righty. So I think at this point we should wrap up. We have a 15-minute break. will commence at, I have to use my cheat sheet and my glasses for this, we'll be commencing at 10:45 here with a second pair of people who will be speaking specifically to the nature of sample returns. Both of them have experience not only on OSIRIS-REx, who they're speaking to today, but also one was part of Genesis mission and one was part of the Stardust mission. That will start at 10:45 here, 12:45 Central Time, and let's see, that would be 1:45 Eastern Time. So until then, have a nice little break, and we'll see you. And I hope some pop flies are happening in the meantime. Don't forget, keep working on your projects there. Thank you.